And welcome to day 4 of week 1. Somehow we are already on day 4, and I have lots of great stuff in store for you today. But what you can already do, you can already write code to call OpenAI on the cloud and Ollama locally. You can compare the strengths and limitations of frontier models and contrast them. And by the end of this lecture, you'll be able to talk about how incredible the way that transformers have overtaken what we do in the field of data science. You'll be able to talk about things like agentic AI, context engineering, agent loops, the latest hot topics. And most importantly, you're going to understand the basics like tokens, context windows, parameters, API costs. And you may be very much familiar with this already. This might be old hat to you, but I always hope to sprinkle in something different to give you something new to think about. So even the people that know this stuff well, hang on in there. I still hope to give you something useful today. But first, before anything else, I know you're wanting to know what happened from this big competition that we ran. What came of Outsmart? Who managed to outsmart the others? Let's go take a look. And I have it running on this tab here. I'll give you a drum roll, prepare to see who wins. And the winner of this particular run was Charlie, which Charlie was being played by Grok 4. Grok 4, known for being perhaps one of the more devious of the models, did in this occasion manage to triumph. With 14, you'll see that it was actually pretty close. The one that did worse down here was Drew at the bottom. Claude's Sonnet coming in last place did not do very well, but it's quite wordy about it. All this stuff. But you'll see that Charlie was ultimately the most successful. Charlie followed by OSS. Followed by GPT-5 in third place, and then finally Drew. And there you see the chart of how it went. And for a while there, actually Drew was the winner, but then the others ganged up on Drew. Fascinating. I hope you enjoy running this yourself, get some insight into it. That's what it's all about. Very enjoyable. And when you're doing it, you can also go to the Swizzly over here on the left. This is also on the main site. If you open it up and press calculate rankings, it takes a second. There's been more than 2,000 games of this played, and you'll see that right now Grok is at the top, but I've only played 3 games with Grok, and it's won all 3 of them, so it comes up very strong. And you can see how some of the others did, but because I haven't played enough games with different ones, it's not, you have to look for the ones which have the most games. Claude 3.5 Sonnet did the most games as the one that really rose to the surface from playing lots and lots of games. So it is actually the one that came out strongest from my public website, where you can play all of them. But the rankings is kind of fun to see. You should give that a try. You can also see the repos, see the code to learn more about what I did, and also read a blog post I made about how I wrote it and some of the tactics that you can work on. And should you wish to make your own variant of the game, there's some ways to do that. You can also run it locally to try out any models that you wish. Anyways, use this as a chance to learn about models, but meanwhile, we've got to press on with the course with week 1, day 4. So we spent some time now with GPT, and I'm sure you spent lots of time with ChatGPT, and you're probably familiar with the fact that GPT stands for generative, is the G, which means that it's a model which is responsible for generating tokens or predicting what should come next after a sequence of inputs. Its P stands for pre-trained, in that it's been trained off tons and tons of data scraped from the internet and from all sorts of sources, controversially. That is the P in GPT. And of course, the T is transformer. GPT, the generative pre-trained transformer. So what exactly is this transformer thing? So I'm not a big fan of teaching tons of theory before you get stuck into stuff. So what I'm not planning to do now is tell you about the innards of a transformer. And I know some of you will be disappointed because I want to know about decoders and self-attention layers and blah, blah, blah. The way that we're going to do it is that over the course of the next 8 weeks, I'm going to be showing you deeper and deeper glances into the insides of a transformer so that you get a better sense of how it all holds together. Because the way that I like to teach theory is through practice, through putting things into action, looking at the code, seeing what this transformer actually looks like as Python code. But for now, what I want to do more is tell you the story of the transformer, give you some intuition for what it is and how it fits together, so that the rest of the next few weeks all fits into place. And it all starts a long, long time ago in 2017. Not that long ago at all. In 2017, a bunch of scientists at Google put out a paper that's called Attention is All You Need, which I've linked in the resources. And the naming was because there's a sort of series of papers that are named in the style, something is all you need. And at the time, it's clear if you look at the paper, and I do recommend you do look at the paper, even though it might not make sense initially. But as I say, linked in the resources, look at the paper. The thing to keep in mind is that it's very evident that the scientists that wrote this paper did not realize what an extraordinary discovery they were making or how it was going to change the years ahead. They didn't realize it. They thought, oh, it's a bit of an optimization. There's something good that we've realized here. And that's at the core of the paper. Attention is all you need. So what was the paper about? Well, the paper was about describing a particular structure of a kind of data science model called a neural network or a deep neural network. And I know that this is old hat to some of you, but just give me a couple of minutes on this. So some time ago, we used to work with traditional data science, and these are models. They are statistical models, mostly, that try to predict some outcome based on some parameters, some controls, and it learns how to set those parameters by looking at lots of examples of data. That's, very broad brushstrokes. So if you're trying to figure out what kind of credit score someone should have that's going to take out a loan, you might look at various factors about that person. And then you might look at a lot of data about different people with those different factors and what their credit scores are. And by comparing your actual data of real world examples of people and credit scores with this new person, you can estimate what the credit score should be based on all of this training data, as it's called. And that is a sort of traditional data science model. And sometime, actually in the 1950s, like a long time ago, someone had the idea of building a special kind of data science model that was loosely inspired by the human mind. Only loosely. It was called a neural network. The idea was that it was, rather than one statistical program, it was lots of statistical programs that were all kind of connected together in some way, sort of playing a nod to the way that the human mind has lots of real neurons, human neurons that are connected together. Similarly, the neural network had lots of little algorithms called artificial neurons that were all connected together. And it turned out to be a very effective way to learn different patterns in data and be able to make good predictions about things like credit scores. And the neural network has something of a storied history, a checkered history of times when it seemed to be very much in vogue and people saw tons of promise, and times when it seemed to not show so much promise and fall behind a bit. And there were various breakthroughs along the way, and most of the breakthroughs are around ways to work with larger neural networks that could take more training data and be able to detect patterns even more deeply. And hence the expression deep neural network or deep learning, which was about building these very, very deep sets of these neurons connected together. They're actually sort of stacked on top of each other, connected together. And the more of them there are, the deeper this became, the more stacks on top of stacks, and the sort of more intelligent these neural networks turned out to be. But I'm getting somewhere with this, I promise. In 2017, Google scientists came up with a new way to organize these neurons, this neural network. It's called an architecture. The architecture is just the approach you use to connect these things together. And the new architecture was especially good at handling sequences of inputs and being able to look back on those sequences and figure out what parts of those sequences really matter, which was a type of layer in this network called a self-attention, an attention layer. And this idea, a layer that was able to figure out what should I pay attention to in the input sequence, turned out to be a huge step forwards. It allowed them to work with much bigger neural networks and much bigger data sets in less time and scale more effectively. And as I say, I know I'm being very hand-wavy on this. We will get more detailed later, but that's the intuition. And in 2018, where Google had really led the field of inventing this transformer architecture, OpenAI, at the time of a small, almost unheard of company, came out with their transformer called GPT-1, the Generative Pre-trained Transformer 1. And it was okay. It was quite basic. And then a year later, they came out with GPT-2. And I think I first really noticed GPT-2. I remember 2020 GPT-3. I had this long argument with my dad about GPT-3 when I was saying, this is something huge. You got to look at this. This is big. He was like, I don't, it's just statistics. I'm not surprised. I also partly felt that way too. We were all caught off guard, even practitioners in the industry, when ChatGPT came out in 2022, which was using a version called GPT 3.5. But importantly, it was also using something called RLHF that I alluded to, I think, yesterday, which is about an even better way to make it not just think about extending a sequence, but also work in a chat mode with a user prompt, a system prompt, a user prompt, and its response, and be trained in that way. And that was ChatGPT. And then, of course, GPT-4 came out in 2023 and was like, whoa. And then 4.0 was last year, the multimodal version. And now, of course, we're on GPT-5. Maybe you're on GPT-6. But the rest is history. That is the extraordinary, astonishing rise of the transformer. And we will cover more aspects of the architecture itself in the coming weeks, but that's enough for now, one step at a time. The one point I want to make, though, is that we don't believe that there's anything super fundamental about the transformer architecture that means that it had to be discovered and that we wouldn't have things like GPT-5 or Claude 4.5 Sonnet if we hadn't discovered the transformer. The transformer, it's an optimization. It's a really clever approach that allows us to scale, train with more data, with more parameters in a more efficient way. Without it, it might have taken us longer to get to the point we're at. It might have cost more. The API cost that everyone complains about might have been 10 or 100 times more. The transformer allowed us to do this faster and cheaper. But it's not like there's anything about it that's somehow fundamental to what it takes to predict tokens. It's more of an efficiency play. That's a way to think about it anyway. And there are alternatives to the transformer architecture. There are state space architectures, if you're familiar with them, and there are hybrid architectures. There's all sorts of stuff going on. As yet, many of them are sort of on lockstep with the transformer, but none of them have yet proven definitively that they are superior to the transformer architecture. So it still remains today the predominant architecture that people use for LLMs. But there are others. And as I say, important to keep in mind, we don't believe there's anything fundamental about this attention thing. It just happened to be really efficient.